So we should work on chapter 5 stuff. We'll do a quiz Friday, the second half of class. I think the quiz will probably have some integrals that involve U-Substitution, which to me is 5-5 and really kind of 5-7. 5-7 specifically seems to focus on the log function, the natural log function, but to me it's just another function. It could be anywhere. Are you guys working on 5-5 at all? Can we start there? Is there anything you want some help with in 5-5? Yes, ma'am?
Just the pattern I recognized or realized, whatever.
Yeah.
Is there always going to be a common factor? Like when we were working on it the other day, we found that it was, you said, are you happy? Is it always like that? Or
right, and when you're not happy, there's ways to fix it sometimes. But I mean, I know what you mean, I think. Look, so a typical U-substitution problem has sort of the pattern that whatever you're calling U, the derivative is also kind of sitting there. Now, so do you see that pattern here? I mean, what would you call U, you think? And after doing some problems, maybe you're getting a habit of, I've been preaching a lot of little hints about U, but U is usually inside something. So maybe U is inside the square root. So then here's your thoughts. If U is an x cubed kind of thing, then du will be the derivative, which will be an x squared kind of thing. See, I think all that through almost before I do it, or as I'm thinking. I think about U, I think about du, and I think that I'm going to be happy on this problem. I think this problem is set up nice. I can see it already. And are you guys with me on that? Now the details are, there's a little details about the 3, and so I think a 1/3 will come out, or, I mean, I don't want to do this all in my head, okay? I do want to write it out and watch it happen. So one more time, let's do this, or not one more time, but if I let U equal 1 plus x cubed, I made that decision, and now the first thing I do, almost like a robot, is I should find du. So a du comes from this, regardless of what's up here. Du is the derivative here. Du is 3x squared dx. And then you're right. At this point, I ask you, are you happy? And the answer is yes, regardless of your personal story. You are happy mathematically because the x squared dx is in this du, and your problem kind of had this extra x squared dx here. See, if you were going to replace this, you were going to have a square root of u, and then you were going to have this extra junk, this x squared dx, and I need it. I don't need it there. I need it replaced. I need it gone. Well, thank you for the du, because the du is going to help me get it gone, right? That's a lot of different ways of talking there, but what I'm saying is, when I see that x squared dx, I see it here. I like to solve for it. So I'm solving for x squared dx by dividing by the 3. So I didn't really solve for dx. Sometimes when I see some connecting stuff, I solve for that. I solve for x squared dx because that's what I saw up there. And so now I'm going to replace the circled x squared dx with what it equals. And what does it equal? 1/3 du. So I replace it. I can put the 1, but I like to go ahead and pull the 1/3 out. I mean, it's here, but I can pull it out, and then it's a du. And now now it's a new looking integral. It's really the same integral, but you've performed this awesome change of variable game. The change of variable game is called U-substitution. It's also called a change of variable game, but you did it correctly. We did great. And now you have an integral that you can do. It's the square root of u, and we know how to do that. It still takes a few little steps. I mean, it's, you know, what is it? It's u to the 1/2. Okay, so all I did there was rewrite it. But now I'll do it. I'll add 1 to the power. It's just a power rule. U to the 3/2 times 2/3. Don't forget the 1/3 plus c, and you're done. You know, again, once you integrate, the integral symbol is gone. And you got a plus c, and you're finished. You're done, except for one last little thing. You don't leave your answer in u's. U was just a temporary change of variable, so you always go back to the original variable. So, so this is actually a 2/9 something to the 3/2. Oh, that's my u. 1 plus x cubed to the 3/2. So that's a classic U-substitution example. I mean, he's classic. And I want to make this point. You guys, listen to this. I mean, I haven't been doing this. I've been trying to do U-substitution problems that I can do. I want to compare and contrast this a second. Listen, you can't do this problem. You cannot do this problem. It's impossible. And maybe that's sort of a realization for students. And even though I've already kind of warned you about that, you know, I said 2 or 3 times now, I think, that when you learned all your derivative rules, you can take the derivative of everything. But when you try to do antiderivatives or integrate, it's not everything. You can't just find the antiderivative to anything. And so a lot of integrals you just can't do. Maybe that's why we bothered to teach you the rectangle stuff, because you can't do this one symbolically, and if you really wanted to do it, you might have to add up some rectangles or approximate it somehow, because you really can't do it analytically. And why not? Okay, well, I mean, you might try to do the U-substitution. You might think it's a U-substitution, but the du is 3x squared dx, and there's no way I needed that. See, this was nice. I'm glad they had this extra x squared. It helped me fit my du into the problem. I've got no way now of fitting this du into the problem. I mean, I got the square root of u. What I need, when you do change it to u's, you definitely change the dx to du, but it's not just an automatic, oh, dx is du. Of course it's not. It's this. du is 3x squared dx, or 1/3 du is x squared dx. Or if I wanted to solve for dx, what's dx? What is dx? du over 3x squared. Okay. All right, watch this. This is du over 3x squared. You know, there's nothing, I'm not worried about the 3. I can pull it out like a constant, but I've got this x squared in here mixed with my u's. That's not good. You were trying to change the variable from x's into u's, and you really kind of can't. Well, maybe you could. Watch this. This, again, I think I made up a terrible problem here. I think I made up a problem you can't do. But if you're trying to do it, I want to show you what you would do this. You would say, oh no, I got x's mixed with u's. I got to get rid of those x's. Can I? Maybe I can solve for x. Is there any place I could solve for x? Maybe right here. What if you subtract 1? U minus 1 is x cubed, and then x would be the cube root of u minus 1. So now I know what x is. I can replace x now. Okay, so now I've got this square root of u. I've got this du. I'm going to pull the 1/3 out if you don't mind. Now what about this x squared? Well, what is x? This thing. So I have this thing squared in the denominator. All right. This cube root of u minus 1 squared in the denominator. Well, anybody know how to integrate that? No. Maybe you need a U-substitution to do that. There are times when you do a second U-substitution, I would call it W. I mean, you need a different letter. You can't, I would call it W or something. So I could go explore a new, now I could do a W substitution. I could try to work on this. I think I would go round and round in messy, messy circles, and I would get stuff that I can't integrate. So I did do the change of variable process, and I had to get creative. I had this extra x squared, but it's leading nowhere. I mean, I can't integrate that, and I don't want to go any further. Well, what's my point? My point is, can you see the difference in these two problems? And can you, even though this one has this extra x squared, it's a much nicer problem. We needed the extra x squared for the du. I mean, so this is a beautiful problem, and this is not. And it has to do with the du relationship. It has to do with the importance of the du dx relationship. Now, let me try another one. Hang on. Watch this one. Okay, watch this one. Here's another one. This one doesn't quite work out too nice, but it will work out, I think. Okay, watch. So what do you think u is? This is a good problem. This is a little more advanced problem, but it's okay. But we abandoned this one. This one just got abandoned. We couldn't do it. Okay, on this one, you let u equal that 5 minus x. Okay, I agree. So now I need du, you guys. What's du? The derivative. Negative 1 dx. Don't forget, you kind of need the dx because that helps you replace the dx. So negative 1 dx, or negative dx. Okay, good. I'm going to start replacing this stuff. Here I go. Here I go. I run into the 4, and I like to say, let's pull the 4 out. I mean, you don't have to pull it out. You could leave it there, but I like pull out the constant if you want. I run into this x, and I'm not sure what to do with that x. So temporarily, I'm going to leave it there. Let's see, what's this? Square root of u. And now the dx has to turn into du, and that's not too hard. Dx is, if you move the negative sign over, dx is negative du. Let's see. So the dx gets replaced with negative du. So by the way, that doesn't mean you're subtracting. It gets replaced with a negative du. You're multiplying by a du. I think I'll take the negative sign and filter it all the way out front. You okay with that? But again, here I am. I got x's mixed with u's for a second here. This is not a good place to be. We need to fix this before we move any further. Can we replace x somehow? Can we go back? We go back to our original declaration of what u is, and maybe sometimes you can solve for x in terms of u. I think I'll do that. I'll solve for x in terms of u. I think what I'm going to do is add the x over here and subtract the u over here. So I see that x would be 5 minus u. Are you guys okay? I solved for x. Added the x, subtracted the u, and that's it. So that x can get replaced with 5 minus u. Kind of like I did this one, except this one led to a mess. This one will be doable. Here we go. I'm replacing this x with what it is. What is x? 5 minus u. Multiplied by this square root of u. And now you can actually do this problem. We can finish this problem. But I'm going to stop and see if you got any questions. Yes?
When you have a negative 4 out there on sort of the integral, shouldn't that be negative 1/4?
No. This 4 just slid out in front. It's a multiplied 4. You can pull it out in front of the integral. You don't change it to a 1/4. I don't know. Nope, it's just a 4.
Really? But isn't that 4 over 1 and then you and they multiply your side? I mean, divide your side. Therefore,
yeah, there is no other side. I'm working on this integral, and I pull out a 4. Yeah, maybe you're mixing some thoughts, and maybe I can help you figure out which thoughts you're mixing up there. Well, watch this. Over here, this problem had a 1/3 come out in front. Now, the 1/3 wasn't here. It wasn't a 1/3 here. And if there was if there was a 7 here, I would pull out a 7, whatever. Where did the 1/3 come from? The 1/3 came from me replacing the x squared dx. So the circled x squared dx got replaced with a 1/3 du. It came from this derivative being a 3. That's what led to the 1/3. So this problem had a 1/3 come out, and it was from the du. This problem had a 4 come out, and it wasn't about the du. It was just about a 4 sitting there. Let's pull a 4 out. So it was a different story about the constant.
I don't understand how come sometimes you're gonna flip it over, sometimes no.
Okay, so I'm not flipping anything over. Look, I'm solving for dx. I'm solving for x squared dx. You understand that this is a 3x squared. You understand this?
Yep.
Yeah. So there's a 3 here. I did flip it over, but it wasn't about flipping it over randomly. It was about solving for this. So by solving for this, I ended up with a 1/3 times du. And when I replaced this stuff in the integral, this got replaced with a 1/3 du. Now, when I pull it out, I'm not flipping it over. I'm pulling out the constant that's multiplied. I pull out the constant that's multiplied. It is the flipped over version of this, but this is the explanation why. Right here is what explains why. Right here. Any other questions?
But you weren't solving for x right there.
No. Any other questions about this setup? Yes?
Why isn't it sometimes you just have to solve for, well, you have to find all u and du equals and all that, but sometimes you gotta go further, like we did right there, where you have that u and you solve for x and then equation.
Yeah, why is it sometimes you do and sometimes you don't? Right, yes, the answer is there's a lot of variations, there's a lot of problems that can be presented to you. And you have to get creative, and there's not just maybe one robotic method. There sort of is. I mean, the robotic method is you call something u, you find du, and you replace everything in the integral algebraically correctly. And sometimes when you have extra x's hanging around, you have to solve for u and replace those x's. So that's what happened in this problem. This was a u. This was a square root of u. The du was negative dx. I replaced all that, but there was this extra x still hanging around. And so I had to replace it with what it is in terms of u.
Oh, okay, that makes sense.
Good. So I had to replace that x with what it was.
Right, because either we have all x's or we have all u's.
That's true. Having this little temporary place with x's mixed with u's is not good. Right, we have to get past this. We have to get out of this. And you see me pull out constants, never pull out an x. Why not? It's not a constant. You're allowed to pull out constants. You never pull out an x. It's not a constant, right? So we got to deal with it, and that's how we have to deal with it. I call this slightly creative U-substitution. You had to call something u, and then you had to play around a little bit, solve for x in terms of u to get here. You had to get slightly creative. Hey, how do you finish this? How do you finish this? Distribute, then integrate. That's good. A lot of students will kind of screw that up. They kind of make up their own integral rules, and I'll integrate this stuff and I'll integrate this guy. You don't ever integrate a product. You never integrate a product. Nobody ever told you could. Some students kind of do it on their own sometimes, and it's a bad habit. So what do? You never integrate a product, so that means you better always distribute your product and then integrate each term. So you're right, if I distribute the u to the 1/2, it becomes a 5 u to the 1/2 minus a u to the 3/2. Now it's two separate terms, and now I can integrate. So now I'll integrate. The -4 is out front, and here we go. That's u to the 3/2. When you integrate, you add 1 to the power, and you divide by 2/3, or no, you divide by 3/2, which means you multiply by 2/3. There's a 5 right there, and that guy is done. minus, you add 1 to that. When you add 1 to that, you get u to the 5/2. And then you multiply by 2/5. And now that guy's finished. Put a plus c and you're finished. Well, you're not entirely finished. We should put back in our x's. I'm going to help you here. I'm going to leave the -4 out front, but I'm going to call this 10/3, and then it's something to the 3/2, and then minus 2/5, something to the 5/2, and plus c. And what is that something? It's called u, but what is u? Oh, there it is. 5 minus x. It's pretty wild, isn't it? U-substitution, man. It really opens up a bunch of new integrals that you could never do before. It's a cool technique. It's a powerful technique. It opens up a whole world of integrals you could never do before. But there's still some integrals you can't do. Now, I don't want you to... so we're doing some good... Now we just stepped into some good, more difficult, sort of advanced U-substitution problems. Don't let you forget the easy ones. Watch this. Here's an easy U-substitution problem. Really easy U-substitution problem. I don't know, if you didn't think about U-substitution, I don't know, first of all, you need to understand how easy this integral is. It's the integral of a secant squared, and the integral of a secant squared is not really weird. It is he's a famous derivative, therefore he's an easy antiderivative. The answer is tangent. Thank you. So the answer is tangent. I guess I can pull the 5 out. Maybe I could just say it's the tangent of 3x. Maybe I could just say that. The truth is, you can't just say that. I just made an error. It's a kind of a bad error. Technically, is there something you should have called u? What should I have called u? The little angle inside the trig function. If the little angle inside the trig function, if it's more than just an x, then you better call it a u. So that little 3x, I should have called that a u. What would have been the result? Would that have changed anything? Would it have changed anything? What would it if calling u, would that have changed anything? Maybe you need to do it to see whether it changes anything. I was thinking you would figure this out in your head that, yeah, there is a mate. What would happen? Without maybe doing it. I don't know. Thank you. A 1/3 is going to pop out of here. That's what's going to happen. Why? Here's why. You called u 3x. What is du? 3 dx. Please solve for dx. When you solve for dx, you get 1/3 du. So when you replace this integral, so you're going to get this 5 out front. This is the secant squared of u. And when I replace the dx, what do I replace the dx with? A 1/3 du. I'll put the du there. I'll put the 1/3 out front. And now this is tangent of u. But you can see now that a 1/3 came out front. And maybe you knew that all along. So there's the proper answer. A 1/3 popped out. How come a 1/3 popped out? Because you had to do U-substitution. And the relationship between du and dx has this 3 here. And that's the relationship. And it results in a 1/3. Yeah, that you didn't really see in the problem, but you see it here. Right. So that's easy. That's baby little U-substitution. That sometimes you might do it so fast in your head that you make that error that I made. Listen, anytime you call something u, you got to do the du. Some people like to skip over this step because they think they can just do it in their head, maybe. I don't know. You could do it in your head if you do it correctly. But you need this du. Anytime you call something u, you need du. And you need to see what happens. Yes, Carlos?
Over there in the second part, where you have 5/3, 51, secant squared, du. What was the reason for writing du instead of the 1/3 du?
I did write 1/3 du. I did write 1/3 du. I just wrote my 1/3 out here.
Oh, okay.
I could put it here and then the next step slide it out here. But I like to pull it out front as I do it. Okay. So you're right. This is a 1/3 du. And I did replace it. It's right here. But I put the 1/3 out here and I put the du here. Right. It's a multiplied constant. Those multiplied constants can come out front. Yep. Here's a good one. This is a good problem. Some students, every problem is different, so you really got to think your way through these U-substitution problems. They're all got their little different twists and turns. I mean, there's a commonality in it, and I've been trying to teach you the common themes, but some problems are a little different. Any ideas on this one? I mean, I've been saying the angle is the U. On this one, I want to do something different. On this one, I want to let U be the sine function. The entire sine. I want to let U equal the sine of 4x. And you'll see why as soon as you do du. I think you'll see why. What is du? The derivative of sine is cosine. The chain rule, though, when you do a derivative, you got to remember it spits out a 4. The derivative of sine 4x is cosine 4x, but I got to do the chain rule, which spits out a 4 dx. So, are you happy? Yeah, you just called this u, and your du wipes out the rest of that for you. It is off by a 4. So what am I going to do with this extra 4 here? I'm going to divide by it over here. 1/4 du equals the cosine of 4x dx. And now I can replace this integral, okay? It's replacement. It really is replacement. Some people think this is mysterious. How does he... It's total replacement. Using this as a guide, you replace this crap. Okay, so what's this? A u? That's a u. That's a u. What is the stuff in the box? The stuff in the box is right here. And what is that? 1/4 du. Okay. I'm going to pull the 1/4 out, and I'm going to write du right here. Awesome. Can anybody integrate a u with respect to u? You know how to integrate a u? Yeah, u squared over 2. U squared over 2. Cool. Yes, Carlos?
What did you just get done doing there?
Okay, I replaced everything in this integral needs to be replaced. So what do you replace him with? What is it? What is that? Replace him. Replace him. What is it? What is this? What is this? I got to replace it. What is it? What is it? Do you see it?
Sine 4x.
Yeah, what is it? What is it equal to? What is it equal to?
Cosine 4. Oh, wait, no, it's you.
All right, so what is he? He is u. We called him u. So that's u. So I replace it. I called it u. All right, what about this stuff? I got to replace all this stuff. What is this stuff? Do I see it? Do I see it anywhere? What is it? Oh, here it is. What is this stuff?
1/4 du.
So I replaced it. 1/4 du. I put the 1/4 out, but
wait, how come you didn't put the...
I don't know, dude. So somewhere in your brain, you've got some memorized thing that says flip something. And that might be okay if you get it if you put it in the right place in your brain. But right now, it's kind of not in the right place. You're just saying flip something for no good reason. So maybe you should forget flipping things. You should try to understand the process.
But the problems in the whole word, they all have these examples. I mean, not every single one of them, but most, these are problems in 5.5. And these parts of the problems, they do them, or they have 4, and they break it out as 1/4.
Well, that is what happened. Do you see the 4 and how it came out as a 1/4? Right. So it did happen. But this is why.
But why you have 1/4 integral on u/du though?
Because I replaced this with what it is. And what is this? This is 1/4 du. That's what this was. How do I know that? Because I did these steps over here. This is here it is. It's a 1/4 du.
Oh, okay, but if it's a 1/4 du, then why is it still 1/4 when you break it out in the integral?
Because I replaced this. I replaced this with what it is. And you know what it is? It's a 1/4 du. That's what it is. And now this is a constant multiplied in your integral. And what do you do with this constant that sits in your integral? You can pull it out front. And when you pull it out front, you pull it out front. You don't flip it. You pull it out front.
You pull it up front when it's in front of a constant like du.
You're allowed to pull multiplied constants out in front of the integral. So I do that when
So if it's a constant, it's pulled down. If it's something that's being multiplied, by x or whatever, then that's when you got flip it over because try to get the x by itself and the constant of the way.
I don't know. The flipping over comes from right here. The flipping over comes from solving for dx, or solving for the cosine of. The flipping over comes from when I decide I'm going to move this 4 over here. I'm going to divide by 4. Then it gets flipped over, right? It's from here to here is when it gets flipped over. And if you understood why it gets flipped over, then you don't have this random flip over thought in your head. You need to understand these steps and then this replacement. That's it. And that's true, for everybody, right? I'm talking to him. He's asking these questions, but we all need to understand this. And this is where I keep saying some students don't get it. They stare at this, they don't understand what I'm doing. They think I'm doing some kind of magic replacement. It's all about understanding these steps and understanding what equals what and how you actually replace these items. See, this integral, through these substitutions, this integral turns into this integral. And I think it's easy to understand when you read this. Who got replaced by what? This was my u. This turned into u. This was my du. Not exactly. Excuse me. This was 1/4 du. So I put my 1/4 du here, and I pulled the 1/4 out. It was replacement from these ideas right here. Hey, now you're going to integrate. It's u squared over 2 plus c with a 1/4 multiplied right here. So we're done. 1/8 u squared. What is u? The sine of 4x squared. You could write it like that. If you remember, when a trig function is squared, we write it like this. So anyway, these are the same. But when a trig function is squared, we write it like that, of course. That was a good one, man. It was kind of a unique situation. You let u equal sine, du is cosine. I could see that coming. I could see if I let u equal sine, du is cosine. So I decided to go with that.
Did you put in the same place of cosine?
Oh, I could have let u equal cosine, and du would have been sine. Actually, it would have been negative sine, and so a negative sign would have spit out of this, but you're exactly right. I could have had a different looking answer. When it comes to trig, you can have different looking answers because of the trig identities. Sine squareds might look like cosine squareds sometimes because there are identities that equate the two, right? Yeah, there's the more advanced ones, kind of in the 60s there. They kind of got some advanced ones. And then they got these definite integrals. Let's try this guy. This guy looks nasty. I'm in 5-5. This is 79. 79 looks kind of nasty. It's e to the 3 over x all over x squared dx. Is this right? Wow. From 1 to 3. Look at that. I mean, that's a scary looking problem. By the way, this one turns out to be a definite integral, so I need to integrate it, but at the end I will evaluate it. When I see an e function, I mean, this is not always the case, okay? It's not always, but when I see an e function, my brain is thinking of this rule, you know? The integral of e to the u is e to the u plus, you know? So, so maybe, you know, I don't even have to think too hard. Maybe I should, whatever the exponent is on the e, maybe I should call that u. You know, just. So I'm thinking that my u should be that 3 over x. Now I got to do that. Now I got to do this derivative. So hold on a second. This is bothering me. I'm going to move that x up and call it x to the negative 1. Is that okay with you? So now I'll do a derivative. Du is negative 3 x to the negative 2. Keep in mind you're doing a little derivative here in the middle of doing an integral. You're doing a little derivative here. I'm going to rewrite that. I'm going to rewrite that as negative 3 over x squared dx. That's what he is. And then I can try to ask you this question, are you happy? Yeah, you are happy. Why are you happy? Well, let's see. If you start replacing this stuff, what you have is e to the u. And then you have this, which again, the dx is always off to the side. And if it's off to the side, you can consider it in your numerator. It's never considered to be in the denominator, and you never want to end up with it in your denominator. It needs to be off to the side or in the numerator. So what this is a dx over x squared. Y'all see that? Do you see a dx over x squared over here? So I could replace that with this. This damn negative 3 is in my way, though. What should I do with that? Divide by it. So negative 1/3 du is 1 over x squared dx, and that's what I see up there. So I'm replacing that circled stuff. I already replaced this, e to the u. Now I'm replacing that circled stuff with, negative 1/3 du. I'll pull the negative 1/3 out here, and I'll put a du right there. This is the game, you guys. This is the game. I keep, over and over and over again, I'm doing this. And you need to do it. You probably should do a bunch of homework. I mean, this is, I don't know. It's cool. You can watch me, but you gotta practice this process. Hey, I'm ready to do this. How do you integrate e to the u? So we're done. It's e to the u plus c. There's a negative 1/3 in front, multiplied in front, and the problem's over. Oops, wait a minute. This problem had bounds, definite bounds here. And so I don't need the plus c. What I need is to evaluate it from 1 to 3. But now hold on. What I just wrote is actually kind of bad. I mean, what's tempting here maybe is to take that 3 and that 1 and plug it in and finish this problem. But hold on. That 3 and that 1 are x values. And they need to be plugged back in for x. And I'm still temporarily in u's here. I need to get back to x before I use the 1 and the 3. So this, I don't know, writing that ain't too bad. I need to hurry up and get back to x. What was x? What the hell was u? I mean, 3 over x, right you guys? 3 over x. Okay, now I can evaluate it from 1 to 3. That's all. Just get back to x's. These original bounds are x bounds. Get back to x's to use those bounds. Here we go. You plug in a 3 and you get negative 1/3 e to the first, or just e. Minus negative 1/3 e, when you plug in a 1, you get e cubed. We're finished, you guys. That's the answer. I could try to make it look better or write it nicer, but that's the answer. Are you guys okay? You know, what could I do? I could call it negative 1/3 e plus 1/3 e cubed. Yeah, that's better looking. That's good.
So you want to decimalize it?
I mean, no, we like our exact math problems, you know, we like our exact answers. If it was sort of a word problem, a decimal might be appropriate. And you can always decimalize it for fun to see what it is. I'm going to hit pause.